Hi, I'm Ben Ford from Physics Partners. In this short film we're going to look at how to teach specific heat capacity. This film is part of a series to help you with your physics teaching, especially if you're new to teaching, new to physics, or just looking for some new ideas. We'll focus on the common misconceptions that students have and give you some tips for introducing this concept, especially if you're teaching remotely. The meaning of the term specific heat capacity is easiest to understand if we look at an example of it. The specific heat capacity of water, or the C of water, is 4,200 joules per kilogram degrees C. If we analyse these units, this tells us that if we had 1 kilogram of water, which is the same as 1 litre, we wanted to raise its temperature by 1 degree C, we'd need to put in 4,200 joules of thermal energy. Or it takes 4,200 joules to raise 1 kilogram of water by 1 degrees C. This is a great opportunity to do what we call maths last, to use this value here and to see how much we can work out without requiring the students to use the equation at all. So if it took 4,200 joules to raise 1 kilogram of water by 1 degree C, how much energy would be required to raise 1 kilogram of water by 10 degrees C? Most students will straight away just jump to this and see that it has to be 42,000. They've just times this value by 10. Okay, what if we only had 0.5 kilograms of water and we just wanted to raise that by 1 degree C? So again, how do we equate it to the original example? So it's going to be half of this, so therefore 2,100. Last one might be, I'm going to put 8,400 joules of thermal energy into my 1 kilogram of water. How much is the temperature going to change this time by? This time we can see that if it's double this value here, so therefore it's going to have to make the temperature go up by 2 degrees C. This is a really nice way of easing students into the maths, making them use an equation without even having seen it yet, so they can understand why we are using that equation when it comes to it. Now let's move on to the equation. For the main example, this is a use specification point and not a recall, so the students are given this equation in the exam. So we start off with change in thermal energy, how much energy you're putting into the system or losing from the system, is equal to the mass of how much material we have, times by the specific heat capacity of that material, times by how much the temperature is going to change by. We're interested in the units, it's going to be joules for thermal energy, kilograms of course for mass. We've already said that this is joules per kilogram degrees C. Now the change in temperature, you can either measure that in Kelvin or you can measure that in degrees C. Both of these two units have the same interval, so the students will get the same answer whether they use each one of these units, it doesn't matter. If we want to shorten this to symbols, we're going to use E for energy, M for mass, little c for specific heat capacity, then for the change we put delta, and for temperature we're going to say theta. Theta stands for temperature in degrees C. You can use capital T here, but that tends to mean temperature in Kelvin, but students will not be penalised if they put capital T there. So this equation is describing for me how much energy is required to raise 1 kilogram of a material by 1 degrees C. This is a good opportunity to look at some various values of specific capacity. The ones to highlight are copper, which is 385, and aluminium, which is 900. These are the two that seem to crop up in exam questions, and they're most likely to be the metals that you have in your schools to use in a practical. Both of these have very low values of specific heat capacity compared to water, and it's a good opportunity here to do a think, pair, share with your students. And the one I always use is that I put in 10,000 joules of thermal energy and I put that into a 1 kilogram block of copper. I've also put it into a 1 kilogram block of aluminium, and finally I've also put it into a 1 kilogram of water. Which of these three is going to change temperature the most, or the largest change in temperature? Many will quickly see that it is copper which is going to change its temperature the most. This is because it only takes 385 joules to make copper go up by 1 degrees C. So therefore copper is going to rise by a lot compared to water, which has taken 4,200 joules to raise by 1 degree C, so it's only going to rise by just over 2 degrees C. Some students will require you to prove this for them mathematically using the equation that we looked at before. Once I've done this, I'll model a single example of me using the equation, then I'll give my students some time practicing using the equation on mini whiteboards, which if you've time you could pause and practice completing these. The answer to these are 840,000, 50, 1,000, 3 kilograms, 28,600, notice the mass is 5 grams, so I'll need to use 0.005 kilograms. And the final answer, the change is 100 degrees C, so the final temp is 150 degrees C. So our first lesson has been introducing the equation and having students practice using it. The second lesson we'll be doing the practical to find the specific heat capacity of an aluminium or copper block. This is one of the core practicals for most of the main exam boards, and it's one that most schools have the apparatus to complete. I'm going to look at today though a variation of this, and one that can be completed at home for homework or during remote learning. And what we're going to do is find the specific heat capacity of water. All students are going to need for this is an electric kettle and a stopwatch. We'll boil this kettle and then use the equation that E is equal to mc delta theta, and we're trying to find C, the specific heat capacity of the water in the kettle. The mass is easy to find from these variables. We can just say that 0.5 litres has a mass of 0.5 kilograms. If they don't have a measuring cylinder, a student could say that a pint has a mass of 0.568 kilograms. The change in temperature we can find by taking the start temperature with a thermometer if they have one, otherwise they can just assume that the starting temperature is 15 degrees C. The kettle will raise the temperature to 100 degrees C, and therefore our change in temperature will be 85 degrees C. The problem is finding the thermal energy into the water. If we take the assumption of conservation of energy, all the electrical energy that goes into our kettle will go into the water as thermal energy. So we need to turn the kettle upside down and find out what the power rating is of our kettle. My kettle has a range of power rating from 2,520 to 3,000, so I can just take the average power of this, which is 2,760. Then we have to use the equation that energy is equal to the power times by the time, where the time is how long it takes to boil my water. So let's see what this looks like. So I put in my 0.5 kilograms of water. I'm going to switch on my kettle and at the same time start my stop clock. Put on the lid so we don't lose our energy. So my kettle took 1 minute and 16 seconds to boil. So now I've taken my data, I'm just going to use our equation E equals mc delta theta. Energy is equal to power times time. My power in was 2,760 watts. My time was 76 seconds. Remember, time has to be in seconds. So I want to work out how much energy I put in. So it's just these two values plus times together. So 2,760 times by 76 gives us 209,760. Then I'm just going to rearrange this for C. So C is equal to the energy over the mass times by the change in temperature. So the mass that I used was 0.5 kilograms. And our change in temperature was, we got to 100 and we started at 15, so 85. So our energy was 209,760 over 0.5 times by 85. We just place this into our calculator. This gives us a specific heat capacity at our at-home experiment of 4,935.5 joules per kilogram degrees C. Let's go to free sig fig. Thanks for watching this, and I hope this gives you enough to go on the first few lessons of this topic.